Dear students, in this class, let us discuss about the existence of primitive roots mod p raised to alpha. So, let G be a primitive root mod p. G be a primitive root mod p. G be a primitive root mod p means we know that G power phi of p is congruent to 1 mod p. Okay, if G be the primitive root mod p, then G power phi of p is congruent to 1 mod p. G power phi of p congruence means, what is phi of p? Since p be a prime, so phi of p is p minus 1, that means G power p minus 1 congruent to 1 mod p. Agreed? Okay. But what is phi of p square? Phi of p square equals, what is phi of p square? Phi of p square is p square minus p. Okay, p square minus p means it is p into p minus 1. So it should greater than p minus 1. Why? Because p is a positive quantity. P is an odd prime. P greater than 0. So phi of p square is p into p minus 1, that should greater than p minus 1. If g of or if g power phi of p square, if g power or g power p minus 1, for going to that one, if g power p minus 1, if g power p minus 1 is congruent to 1 mod p square, what happens there? If g power p minus 1 congruent to 1 mod p square, then g is not a primitive root mod p square. Why this is so? Because we know that, or we already proved that, phi of p square should greater than p minus 1. Okay. Since phi of p square greater than p minus 1, then g power p minus 1 congruent to, if possible, g power p minus 1 congruent to 1 mod p square, then g is not a primitive root of mod p square. That means g is a primitive root mod p square. G is a primitive root mod p square. Then g power p minus 1. Then g power p minus 1 is incongruent to 1 mod p square. Okay. If g power p minus, g is the primitive root mod p, then g power p minus 1 congruent to 1 mod p. If g power p minus 1 is congruent to 1 mod p square, then g is not a primitive root mod p square. Why? Because phi of p square greater than p minus 1. Therefore, g is a primitive root mod p square only when g power p minus 1 is incongruent 1 mod p square. That is, so this is the necessary argument. The relation g power p minus 1 is incongruent 1 mod p square is a necessary condition for the primitive root g mod p. This is also a primitive root g mod p power alpha. Okay, so g power p minus 1 is incongruent 1 mod p square when g is a primitive root mod p. So, g is a primitive root mod p, then g is a primitive root mod p square only when g power p minus 1 is incongruent 1 mod p square. Okay, so that's a important result. That is, g be a primitive root mod p, then g is a primitive root mod p square if, only if g power p minus 1 is incongruent 1 mod p square. Agreed? That is clear from here. Okay? Right. Now, we consider a theorem. The first part of the theorem, or the theorem states that there is at least one primitive root. There is at least one primitive root g mod p. There is at least one primitive root g mod p G mod P, which satisfies G power P minus 1 is in complement 1 mod P square, hence, not P power alpha, 1 mod P square, hence there exists at least one primitive root mod P power alpha, there exists at least one primitive mod, there exists at least one primitive mod P power alpha for alpha greater than or equals 2. For alpha greater than or equals 2. So the theorem says that there exists at least one primitive root G mod P which satisfies G power P minus 1 is in complements 1 mod P square, then there exists at least one primitive root mod P power alpha if alpha greater than or equals 2. Okay. How? So its proof is, come to the proof. Let G be a primitive root. First it is given G be a, let G be a primitive root mod P. G be a primitive root mod P means we have, that implies G power phi of P is complements to 1 mod P. Since P be a prime, phi of P is P minus 1. Therefore, G power P minus 1 is complements to 1 mod P. Agree? So, if G power P minus 1 is in complements 1 mod P square, then there is nothing to show. Okay, we already showed that if G be a primitive root mod P, then G be a primitive root mod P power alpha only if G power P minus 1 is in complements 1 mod P square. So it is given, let G be a primitive root mod P. So we have G power P minus 1 is complements to 1 mod P. If G power P minus 1 is in complements 1 mod P square, then there is nothing to show. But if possible, G power P minus 1 is complements to 1 mod P square. What happens here? If possible, G power P minus 1 is complements to 1 mod P square. Then we prove that G equals or G1 equals some G plus P. G1 equals some G plus P, which is another primitive root mod P, satisfies G1 power P minus 1 is in complements 1 mod P square. Clear? Do you have any confusion? If G power P minus 1 is in complements 1 mod P square, that is what we require here. Now, come to another possibility. If possible, G power P minus 1 is complements 1 mod P square. Then, we prove that, consider G1 is G plus P. P is any odd prime. Then, P is any prime. Then, which is another primitive root. If G1 is G plus P be the another primitive root, G be a primitive root. If possible, this G plus P another primitive root mod P, then G plus P all power P minus 1 is in complements 1 mod P square. Instead of G plus P, here we use G1. Okay. So, what is G1 power P minus 1? G1 power P minus 1 is G plus P all power P minus 1. Okay. By binomial expansion, it is G power P minus 1 plus, what is the second term? P minus 1 C1, come on, G power P minus 2 into P, okay, plus, what is the next term? P minus 1 C2, G power P minus 2 P square. The next term is P minus 1 C2, G power P minus 2 into P square plus etc. Okay. Right? G plus P all power P minus 1 by binomial expansion. It is G power P minus 1 plus G power P minus 1 plus, G power P minus 1 plus P minus 1 C1 G power P minus 2 P plus P minus C2 g power p minus 3 into p square plus etc. Okay. Consider the first term. Consider the terms. All the terms except the first, including the term p. Here it is p, the next term p square, p cube and so on. So all the term except the first consists of the term p. So it is congruent to, can be rewritten as it is congruent to g power p minus 1 mod p. Okay, congruent to g power p minus 1 mod p. Clear? Why? Because all the terms except the first consists of p, means they are the multiples of p. So g1 power p minus 1 congruent to g power p minus 1 mod p. But what is actually g? G is primitive root mod p, means g power p minus 1 congruent to 1 mod p. So here it is g1 power p minus 1 is congruent to 1 mod p. g1 power p minus 1 is congruent to 1 mod p means g1 is also a primitive root mod p. g1, what is g1? G plus p means g plus p is also a primitive root mod p. So when g is a primitive root mod p for any prime p, then g plus p is also primitive root mod p. Agreed? Okay. Now again, consider this g1 power p minus 1. Now come to this expansion. What about, come to this expansion, all the terms except the first and second consist of the term b square also. Okay. G power p minus 1. Here it is p, here it is p square, and what is the next term? There involves p cube, the next term involves p power 4, and so on. So all the term except the first two consists of p square. Therefore, that can be rewritten as g1 power p minus 1 is congruent to g power p minus 1 plus p minus 1 c1. What is p minus 1 c1? It is p minus 1 into g power p minus 2 into p mod p square. Okay? We already proved that when g is a primitive root mod p, then g plus p is also a primitive root mod p. Now, if g1 power p, if we have g1 power p minus 1 is again congruent to g power p minus 1 plus p minus 1 g power p minus 2 p plus, what is p plus some lambda into p square. All the other terms consist of p square, so it is into p mod p square. Okay. That means again it can be rewritten as it is congruent to g power p minus 1, okay, plus p into p, again there is a term p square. So minus 1 into, so it is g power p minus 1 minus p into g power p minus 2 mod p square. Listen, if you multiply this one, open this bracket, p minus 1 g power p minus 2 p into p, there is a p square g power p minus 2 mod p square. So that is again mod p square. So what means g power p minus 1 minus p into g power p minus 2 mod p square. Okay. What is actually g power p minus 1? It is 1. So means it is congruent to 1 minus p into g power p minus 2 mod p square. So means g1 power p minus 1 congruent to 1 minus p into g power p minus 2 mod p square. But we know that p into g power p minus 2 is always incongruence mod p square. Why? P into g power p minus 2, p into g power p minus 2 always incongruence 0, g into p power p minus 2. Listen. Okay. But what is g into p power p minus 2? G into p power, as p into g power p minus 2, p into g power p minus 2 always incongruence 0 mod p square. Clear? Let's imitate. P square does not divide this one. Okay, since p is positive, p square greater than p, so p into g power p minus 2 is incongruence 0 mod p square. So p into g power p minus 2 is incongruent 0 mod p square means g power p minus 2 is congruent to, that means g power p minus 2 is congruent to 0 mod p. 0 mod p. Why? Why this g power p minus 2 is, since p into g power p minus 2 is incongruent 0 mod p square, is it implies g power p minus 2 congruent to 0 mod p? Means, how this one? So listen, if possible, or if p divides g power p minus 2, if p divides g power p minus 2, p divides g power p minus 2 means p divides g into g power p minus 2. Okay. Yes. That means gp divides g power p minus 1. Okay. That means g power p minus 1 is congruent to 0 mod p square. Sorry, 0 mod p. G power p minus 1 is congruent to 0 mod p. That's a contradiction. Why? We know that g is a primitive root mod p. G is a primitive root mod p means g power p minus 1 congruent to 1 mod p. But over here we get g power p minus 1 is congruent to 0 mod p. That's a contradiction. So when p into g power p minus 2 is incongruent 0 mod p square, then g power p minus 2 is congruent to 0 mod p. That's a contradiction. Okay, therefore, since g power p minus 1 is congruent to 1 mod p, g1 power p minus 1 congruent to g power p minus 1, congruent to 1 minus p into g power p minus 2, so which is incongruence 1 mod p square. Okay, that means g1 power p minus 1 is incongruence 1 mod p square. That is what we recursive. Clear? Means if g be a primitive root mod p, then there exists at least one primitive root mod p power alpha for alpha greater than or equals to. Okay, so when p into, since g be a primitive root, we know that g power p minus 1 is congruent to 1 mod p, and if possible there exists at least one g plus p. If g1 is g plus p, when g is primitive root mod p, then we show that g1 is also, means g plus p is also primitive root mod p. If g power p minus 1 is incongruent 0 mod p square, then surely this g1 power p minus 1 also incongruence 1 mod p square. Okay, therefore the result is finished. Clear? Yes. Now we try to prove another result. Let p be an odd prime. Consider another result. Let p be an odd prime. Then we have, if g is a primitive root mod p be an odd prime, the theorem states this: p odd prime, g be a primitive root mod p, g be a primitive root mod p, then g is also primitive root mod p power alpha for all alpha greater than or equals 1, if and only if g is also primitive root mod p power alpha, where alpha greater than or equals 1, if and only if g power p minus 1 is incongruence 1 mod p square. 1 mod p square. We already see that if g be a primitive root mod p, then g is a primitive root mod p square only when g power p minus 1 is incongruence 1 mod p square. You already see that result. Here the theorem states that if p be an odd prime and g be a primitive root mod p, then g be a primitive root mod p power alpha for all alpha greater than or equals 1, if and only if g power p minus 1 is incongruence 1 mod p square. So come to the necessary part. First we assume that g be a primitive root mod. Let g be a primitive root mod p. That means g power phi of p, since p be an odd prime, so it is g power p minus 1 is congruent to 1 mod p. Okay, right. If G be a primitive root mod P power alpha, G be a primitive root mod P power alpha for alpha greater than or equals 1, then for alpha greater than or equals 1. Alpha greater than or equals 1 means, so in particular G be a primitive root mod P square, put alpha equals 2. G be a primitive root mod P square. So that is, if possible, G be a primitive root mod P square, then we have G power P minus 1 is congruent to 1 mod P square. G be a primitive root mod P if G power P minus 1 congruent to 1 mod P. Here we assume if G be a primitive root mod P power alpha, put alpha is 2, that is if G be a primitive root mod P square, then G power P minus 1 congruent to 1 mod P square. Okay, then here we also know that what is phi of P square? The previous case, phi of P square is P square minus P equals P is P into P minus 1. It should greater than P minus 1. Phi of P square greater than P minus 1. So G can't be phi of P square greater than P minus 1. So G can't be a primitive root mod P square. Okay. So if G be a primitive root mod P power alpha, then G power P minus here, then G power P minus 1 is in congruence 1 mod P square. So the necessary part is finished. Okay. Now to prove its sufficient part. The sufficient part means if G be a primitive root mod P such that G power P minus 1 is in congruence 1 mod P square, then we prove that G be the primitive root. So that is in the next class. So, and the sufficient part, the proof of sufficient part is heavily depends upon another lemma that we will discuss in next class. Okay, thank you.